All right, good morning. Happy week 3, lecture 4, continuing on with soil. Yeah, lab start this week, so that's going to be cool. Who's in the lab right after this? Probably every person here, so everyone else shows up. Okay, well, if you guys are cool, like this class will probably end a little bit shorter or earlier. So if you guys are fine with going there straight after, we don't have to start exactly at 9:30. Your schedule technically says 9:15, I think, is when the lab starts, or 9:20, but 9:25. Okay, yeah. Well, I pushed it back 5 minutes because this class, having to walk over there and maybe get some stuff ready, but everything's already ready over there. So whenever this is over with, we can walk over there and knock it out. It's a pretty quick lab. You are going to have your first homework 1 posted. It's going to be posted after the Thursday's lecture. So just wanted to at least put it on your radar and let you know what's coming. It's not available yet, but you'll have a week to complete that. And it's going to be just on the stuff we've been talking about. So phase diagrams and all that fun stuff, moisture contents, void ratio, and that stuff. Let's see. Did want to just point this out. A lot of you guys have had me before as a professor, and these little weekly quizzes. I know it's really easy to work together and stuff, but there are different questions. Each person's going to get a different question and different answers. And in some cases, I see a lot of people responding to one problem with the correct answer to another one. I don't know if it's because you're just working together blindly, but I at least wanted to remind you guys to read the question fully and make sure that you're putting in the right numbers. And if you are working with a friend, at least make sure you're working on the same problem. So, you don't get a bunch of answers wrong, because it's pretty obvious when I see that. So again, just wanted to throw that out there. It's okay to work together. It's okay to double check your answers, but I'd rather have you guys at least know what you're doing instead of blindly putting in an answer for that. One more thing I wanted to review from quiz number 1, kind of the main points for the first week. Yeah.
When will our grades be posted for the quiz?
Oh, it's not posted yet. Okay, weird. All right, sorry. It'll be right after this class. My bad. Well then, anyways, you guys don't know if you got this right or wrong or not, but what I wanted to just highlight from the first couple lectures, this question, again, the main thing, we use geology in geotechnical engineering a lot, but to summarize it, geology maps and just the input that we get from geologists, they cannot provide a prediction of math, any type of mechanics. It cannot provide strength parameters, and we can't use geology maps for design. We use it for qualitative reasons. We use it to understand what type of soil could be at our site, but it's not an end all be all. So just remember that there's a big distinction. It's important, but it's not necessary for design or not used for design or strength parameters or anything. So yeah, sorry for your quiz is not being posted. I will do that right after class, and you can review the answers. And if there's anything that doesn't make sense, let me know, and we can work through it. All right, today we're going to be focusing still on the components and volumetric relationships. I want to cover and recover a lot of the things that we talked about last Thursday, and go through that same example actually again, but I'm going to go through it a little bit slower and without writing, just so you guys will have it, because this material is really important. Understanding how to find the void ratio and all of those things are going to be important for the rest of the class, the rest of the semester. So yeah, we'll be focusing on that. These are highlights from last week. Again, these soil phase diagram, although we have a conglomerate, a little mixture of solids and air and water, what we can do is summarize this into a 3-phase diagram. So we have volumes of solid, we have volumes of air, and we have volumes of water. And then we also have the corresponding mass of water and mass of solid. And this is a way of viewing and summarizing a soil sample, just by breaking it down into these 3 parts. And what we do when we assume that for this class, we're assuming the mass of air is going to be equal to 0. So we only have a mass of water and a mass of solid. That makes up our total mass or total weight of our sample. We also assume that it's a homogeneous material. So that means that the density is the same. So the solid material, that density is all just one density. Our water is just the same density water. So there's, even though, you know, in the real world, you can probably picture soil and the grains being from a different type of particle or different type of mineralogy, even water being mixed with different types of, you know, salinity or different temperature, so a different density. For this class, we're assuming it's a homogeneous water and homogeneous solid. And we also assume that the solid is non-absorbent. So again, from our materials class, when we were talking about asphalt, you know, these larger aggregate particles have macro pores in it and larger pore space in it, where the binder or the water can be absorbed into our aggregate, you know, our chunk of rock. And that's why we have the different types of specific gravities. Remember, we have like the saturated surface dry and all that stuff. For this, since we're working, that solid material is going to be much, much smaller. It's going to be just little grains of sand or grains of clay. And we're assuming, and it's safe to assume, that they don't absorb water. And that's really important. And it simplifies our equations a little bit more. So we know the water is going to be completely separate from our solid material. So the soil components, again, the reason why we care about all of these volumetric relationships is mainly because density and soil strength are going to be correlated. Generally, as density increases, so the more dense the soil is, the stronger the soil is. And again, like the reason why we do these ratios and assign a quantitative value is it up for this is because these describe physical characteristics of the soil. So we're, again, separating from geology and geotechnical. The geologist would say this has like a lot of porosity or a high porosity. We can actually assign a number to that and then use that as a quantitative index for comparing it to other soils and then also using it for our design. So these ratios also allow us to scale from the investigation size to the site scale, which is really helpful. And that's where this lab is gonna come in handy, because you'll see how we bridge the gap from performing experiments in the lab setting to then applying that to an entire site. You know, the void ratio is the porosity, for example, the volume of voids divided by the total volume. That on a lab scale can then be extrapolated to a site scale. So if we have a certain volume of soil at our site, at our project site, then we can then determine the total volume of voids at the project site, which could be used for like storage of groundwater or anything else, like, you know, strength-wise or settlement estimations. So some of these ratios we've already talked about. The void ratio, that's represented by E. The porosity, that's represented by N. The degree of saturation is just the S. And again, porosity is shown in percentage. Degree of saturation is shown in percentage. We have our water or moisture content. That is shown either by a W or sometimes MC, and that's also in percent. Our unit weights, those are the gammas. So we have gamma normal, we have gamma saturated, and then we have our gamma dry. Our specific gravities, which we covered a lot in our materials class, specific gravity of solids. So G for the specific gravity, the S is the solid. And then relative density, which actually, I don't think we haven't covered this one yet. So this is what we'll cover either today or tomorrow, depending how far we get. But the relative density is also another important one. Relative density is also only used for sand. But again, I don't think we've actually covered this one yet. So we'll go over this in more detail. So some of the baseline parameters to like at least get an idea of what's anticipated in a typical soil are shown here. And again, this is helpful because when you're doing these calculations, especially if you're not like, you know, as familiar with doing these, it's important to understand what range of value your answers should be in, so you can double check your work. Like as we said before, the total unit weights for soil should somewhere be between water and concrete. So I know these are in SI units. Let's see if we were in American units or Liberian units here. Then it would be somewhere between like 80 and 120 PSF or PCF. So that's pounds per cubic foot. So that's generally what we see for the total unit weight for that. Again, everything else aside from the unit weights is nice because they are unitless or in a percentage. So it doesn't matter which units you're in. So again, just to keep in mind the specific gravity of solid, that what that number is saying is how many times that material is denser than water. So around water, thinking about like a water bottle and how heavy a water bottle is compared like a full water bottle. If you're getting a specific gravity of like 100, that means that soil is 100 times heavier than that water bottle if it was in that same size, which doesn't make much sense. Like that's some really dense soil. So again, it should be somewhere between 2 and generally 2.6 is the one that we will cover. A few other things to remember from last week. Let's see. Yeah, the SI unit that you'll see a lot, or the prefix is the mega, so the capital M. And that's 10 to the 6. And the best way to think that is like million. So you'll see that unit used a lot because it's easily, we're usually working with large amounts of soil at a site. So, megagrams is typically more common if you're working in SI units, then you won't be using grams or anything like that. The other one, you guys already know this one, but kilo, the K is times 10 to the 3. So 1,000. So if you haven't gotten those kind of memorized and easy to recall quickly, I definitely recommend doing that because you will see US units, you will see SI units on the FE and on the PE. They switch between those two. That's a big area they like to try to mess us Americans up by doing like a mega versus a kilogram or something like that. All right, so we already went through this example actually. This one was from the last Thursday's class. But I know it can be kind of distracting sometimes with me writing it in, and it's also 8 in the morning and stuff. So I want to go through this again, step by step. And I actually am not going to write it out. I just put it all text wise, in PowerPoint. So just want to let you know, whatever's easiest for you, if it's easier to sit back and listen and actually retain this and then check back and follow this later, or make notes on your own, do that. But just want to give you a heads up. I'm not going to be writing that much, but it's going to be coming in each step by step. So again, what's the first thing we do when we assign or when we are solving these phase diagrams and we're not given a total mass or a total volume? The easiest thing to do is to assume a unit total volume. So that's going to be a value of 1. So whatever units you're working in, if it's in cubic meters, cubic feet, cubic centimeters, whatever it is, just assign a unit value of that number. So it doesn't necessarily always have to be 1 cubic meter. That's important. If you're in centimeters, cubic centimeters, and all your density is given in cubic centimeters here, whatever, then do 1 cubic centimeter, just that way. So 1 unit value. So once we know that, then if we're given the density, then we can find that MT, the total mass. So in this case, since the density is 1.6 megagrams per cubic meter, we know density is the mass or total mass divided by the total volume. We assume that total volume of 1. Then we get a total mass of 1.76. So we've already worked on our outside here, right? Outside of the phase diagram. And now what we need to do is start solving for the things on the inside. So what else do we know from this? We know that the moisture content is 10%. The big area where we're going to be tricked out again, moisture content, porosity, and saturation content is all expressed in 100% or in percentage. But whenever we're doing the math behind it, we always have to convert it back into decimals. So don't leave it in percentage form. The percentage is what you're giving your boss, you're giving your client, you're showing it in that form. But anytime you're doing the math, you need to bring it back into decimal form. So divide by 100 to do that. And we know that the moisture content is a ratio of the mass of the water to the mass of the solid. So 2 independent things. That's why it can be greater than 100%. Now, most of the time we'll see it less than 100%, but it could be greater than 100%. So keep that in mind. So for that, we can set up a system of equations since we know the total mass only consists of two things. The two things it consists of are the mass of the solid and the mass of the water, because again, the mass of air we're assuming is equal to 0. So we have one equation from our total mass, and we have one equation from our moisture content. And now we can solve for either mass of W or mass of water or mass of solid by rearranging these equations. So for example, mass of water is equal to 0.1 times the mass of solid. We plug that in to our equation for that, for our mass of water here. And we can get the mass of solid is equal to 1.6 megagrams, subtracting that from our mass, our total mass, and we can get our mass of water. So these two things, again, thinking in part like parts of wholes and everything, like your mass of water and your mass of solid should never be more than your total mass. So keep that in mind when you're doing these. I know it's all easy like math, but like these are areas that I see people trip up on before, / I've tripped up on it. So we know the mass, and so now we can find the volume. So we have these two checked out. To go from mass to volume, we use density. Or we know the density of the water, and we know the specific gravity of the solid. The density being mass divided by volume, that's the bridge between mass and volume. Our specific gravity is the density of the solid divided by the density of water. We know the density of water in the units we're using is 1 megagram per cubic meter. And so therefore we know the density of our solid is 2.7 megagrams per cubic meter. And this is the benefit of using SI units, because if we were using US units, density of water is 62.4 pounds per cubic foot. So it's not just an easy multiplication times 1 there. So to get volume from our mass and our density, we rearrange the equation here. Again, I think I've showed this. This always helped me remember. What was it, like the density mass divided by volume triangle from 3rd grade. And then you just cover one with your finger. If you need to find mass, then it's density times volume. If you need to find volume, then it's mass divided by density. That just always helped me, and I still use it. It's like the SOHCAHTOA thing from like back in the day, AP calc and stuff. Anyways, from that, then we can easily find our volume of solid, and we can also find our volume of water. So being able to transfer between these quickly is going to be key. We can't find our volume of air from this method because there's no density of air because we have no mass of air. So to find our density of, or our volume of air, again, knowing that we chose to use a 1 unit volume for volume or total volume, and knowing that the total volume is solid, air, and water, we now know solid and water, so we can subtract those out to get the volume of air there. And now we have all the parts that we need. So now that we have a complete phase diagram, we can start plugging and jugging into these equations to solve the things that we need that are asked for in the equation. So first, the dry density. The dry density, again, is the mass of the solid divided by the total volume. So luckily we have all of those things now. And again, since we're in since we assume that total volume of 1, it's kind of simple. So our dry density is just going to be 1.6 megagrams. Always check our dry density should be less than our natural density because we are removing the water. So we're removing the mass, but keeping the volume the same. Our void ratio is the volume of voids divided by the volume of solids. So again, 2 independent things. So it can be greater than 1. So we have our volume of voids and our volume of solid. Important thing with the volume of voids, make sure you're including the volume of air. It's not just the volume of water. And that equals about 0.686. Our porosity, which is N, that's the volume of voids divided by the total volume. So these are 2 dependent things. So it can only be from 0 to 100. Our volume of voids can never be greater than our total volume. And again, volume of voids need to include air and water. I see that a lot, forgetting the air if there is air in it. That's equal to 40.7. And then degree of saturation is the volume of water divided by the volume of voids. So again, two dependent things. So the volume of water can never be greater than the volume of voids. All this stuff, 39.3%. Okay, so that's also, we're asked to find the saturated density. And for saturated, what conditions, what does that mean when it's saturated? We know S is equal to 100, but what's the other condition then that we know that helps us with this math? Yeah, so what does that mean about the volume of air? Yeah, volume of air is 0. Yep, volume of air is 0. So that means that the volume of water is equal to the volume of voids. So since we know the volume of air, we can find the added mass that it would take of water if we replace that air and put water in its place, right? Because we know that the volume of air is 2.4 or 0.247. So if that air volume was filled with water, and we know the density of water, then we can find the mass of water that would be needed to add to that. So that's what we need to do for our saturated density. So saturated density is when all the voids are filled with water. So that's why I added this mass of water is like the hypothetical, the little asterisk here. And that's when all the volume of voids is filled with water. So that's the mass of water that we currently have. So this one right here. And then also the added mass of water that it would take to fill up those air voids. So if with the volume of voids total is 0.407, and we know the density of water, and we can find the mass of water that would be needed to fill up the entire thing. That's equal to 0.407 milligrams, again, because we're using here of SI. So our saturated density is 0.47 plus 1.6 divided by 1. That's 2.0. And again, double check that here. It should always be dry is the lowest, and then the normal or the moist is what it's also called, and then it's saturated. So you should always see it progressing in value. So your dry density is the lowest number, saturated density is the highest, because again, we're just adding water, we're adding mass. So there's another shortcut here, and this is kind of outdated. Does anyone know who that band is? Yeah, all right. That was the alternate stuff back in my day, alt rock. So, but now I don't know, it's like TikTok or something. But there is an alternate solution that is actually a little bit easier, and this helps us develop relationships for this phase diagram that you'll see in your textbook if you fast forward a few pages. So these are what we can do for this instead is if we assume a unit solid of 1 meter, 1 cubic meter. So before we assumed a total unit or a total volume of 1 meter, but if we assume this as 1 meter, then we can do something that simplifies it a little bit more. So if we do this, that means our mass of solid we can determine quickly because we know our specific gravity of our solid is 2.7. So still using the density to go over. If we have our volume of solid, then same thing as we did before, but now we're just starting with the volume of solid. So since we know our mass of solid is 2.7, we know our moisture content relationship. We know our solid, so we can easily find, we plug that in and find our mass of water. That is equal to 0.27. So now we know our total mass because we just add those two things up. So 2.97. Now on the volumetric side, this. On our volumetric side, now we know that the density is staying the same. So if we have our total mass, then we can find that volume that's required to take up that, and that's 1.688 meters, cubic meters. And then we can find our total volume same way by going that way. So there's different ways, and the reason also we do this is for our void ratio. So what I want to show is this equation here. So what we're going to do, or this example, since there's no volume specified, what we're going to do is assume a volume of solid of 1 cubic meter instead. So from that then, let's see about this. Okay. So the value that we're given for this is our void ratio. Remember, our void ratio is the volume of voids divided by the volume of solid. So if we assume a volume of solid is 1 cubic meter, then this helps us out because now we can easily find our volume of voids. This is 0.62. So we know this is equal to volume of voids divided by what we just assumed, 1 cubic meter. So from that, then our void ratio, or sorry, our volume of voids to 0.62. So if we know our volume of voids is, then we can know our total volume too. Oops. So our total volume will be 1, which is our volume of solid, plus 0.62, which is our volume of voids. And that's going to be, oops, no, just make it. So we can still go from volume to mass to find our mass of solid. So just like we did before, since it's 1 and we have a specific gravity, or we have a density here of 2.65, then we know our mass of our solid is going to be 2.65. And then same just as before, our moisture content, the mass of water divided by the mass of solid. Since we have our mass of solid, we can find our mass of water. It's 15. So mass of water is going to equal 0.398. Now we have all of those values plugged in. Yeah, so that's what this is doing here. So we just plugged all of those things in. Again, the void ratio now can be represented by our total volume of voids, since we are assuming the volume of solid is 1. So if we wanted to find our dry density, knowing that our dry density is the mass of the solid divided by the total volume, we know that by rearranging this equation, right, bring this over here, or sorry, no, we don't. Yeah. The previous one. Yeah. Yeah, no problem. Yeah, anytime, guys. Sorry, you don't need to raise your hand. If you need me to slow down or stop, just shout it out. Okay. So to find the dry density, we can create a relationship equation that helps us find the dry density when we assume the volume of solid is equal to 1. So for this, we know that the mass of the solid is just the density of the solid times the volume of that solid. But for this, we assume that the volume of solid is 1. So that means there's a mass of solid is equal to the density of the solid. And we are already familiar with all that. Sorry, let me go back here. Mass of solid is equal to the density of solid. So we can plug this in, obviously the math right here. Gosh, that's the spot that doesn't work. What we can see then is the total volume is just equal to 1 plus the void ratio, right? Void ratio here, 1 here. So if our dry density is equal to the mass of solid divided by the total volume, our mass of solid is equal to our density, because this is equal to 1, our volume of solid, I'm just going to circle that. So this is equal to our density of solid. And then our total volume is equal to 1 plus the void ratio. So that means we have this relationship. Our dry density is equal to our density of solid plus void ratio. This is going to be a really helpful relationship in our labs and in calculations, because we can find our dry density. If we know our specific gravity, then we can find our density of our solid. So then we can find the corresponding void ratio between those two. 5, that's from up here. 1 plus 0.62. We see that's 1.636. So for that, again, up here, I'm just going to write that one up here. So for our density of dry density, we have divided by 1 plus E. So for our total density, it's mass, our total mass divided by the total volume. And again, what we know here is that our total volume is 1 plus our void ratio. We know that our mass of solid is equal to, sorry, that should not be massive. So this is mass total. It should be mass total equals mass of water plus the mass of solid. So again, these relationships here, this was from before. And then knowing that this is just from our moisture content, we can say that our density, our total density, so our natural density is the total, or the mass of solid plus the mass of water divided by the total volume. And then plugging all of these things in, correspondingly, our total volume again being 1 plus E, our void ratio. And then our mass of solid being the density of solid times the volume of solid. We get this relationship here. So this is another important one, because now we know our void ratio and our moisture content can be related to find our density and our dry density. If we plug this in, again, knowing our void ratio and knowing our moisture content, those two have that backwards. Yeah, I figured I had a box. I figured I had that up there too. Okay. So if we had that one from before, then we can also rearrange this, right, by bringing this over here to solve for our density of our solid. And if we plug that into our equation here, and obviously we see something magical happens, these two cancel out and we get this relationship. So this is, again, a really important one and a really helpful one, because if we know our dry density, then all we need to do is multiply our dry density times 1 plus the moisture content, and we can get our natural density. And again, though, this moisture content is important because it's in decimal. So always divide it by 100%. So it's in decimal form. So that's why you add 1. So if it's 0.5 or if it's 15% in this example, then it would be dry density times 1.15. And then that's going to be the moisture. Okay, so another thing it was asking us to find is density when it's 100, or sorry, yeah, the density when it's 100% saturated. And that's our saturated density. Let's see what I had here. So for that, let's say we wanted to find our moisture content when it's 100% saturated. So again, 100% saturation. Is when our voids are completely filled with water. So again, we know from the volume. Oops, the way around. So if we had a saturation value of 0.5, just for example, then that would mean our volume of voids, or yeah. So we'd have 50% filled. So that's like physically what we're talking about, like with a saturation value. So what if we had to find the moisture content when we were in fully saturated, then what we would do is just find the moisture, the MW when the volume of voids is equal to the volume of water. And that's what we've done before. So for that, our volume of voids is equal to 0.62. Right, which is equal to our void ratio. Our mass of water is equal to the density of water times the volume of voids, which is equal to, again, 0.62. This is 1. Then we can find our moisture content at a certain saturation, let's just say 100% saturated. Divided by our solid at 2.65. So what we would show this as is, of course, 23.4. So there's the density when it's 100% saturated. And again, this is our saturated density. As you can probably imagine, there's also a equation that can be used for that too. So again, knowing originally what we had, saturated density is equal to the MW, but then I had that little asterisk there plus the mass of the solid divided by the total volume. And that MW asterisk again is that hypothetical, hypothetical when VA is equal to 0, therefore volume of water is equal to the volume of voids. So when S is equal to 100%, what we found from before, that MW is equal to 0.62 megagrams. So for our SAT, 2.65. Let me keep it straight here. So this is actually 0.62 plus 2.65 for or mass per solid. This is equal to 2.02 megagrams per cubic meter. So what we'll actually see here is, remember from before, we had this relationship. We can use this to determine our saturation still. If we find our moisture content in that saturated state, then we plug that moisture content in to this equation and we can find our saturated. So this can actually be used both ways. Let me actually. So still our solid, and then we go 1 plus the moisture content when S is equal to 100. So what we found before. And then still keep this the same. So the moisture content, in some cases, you may need to determine the density conditions at different moisture contents. Like for example, if your project site is prone to flooding, or maybe the moisture content might drop to 0 whenever, like during a drought or something. And you need to find that hypothetical density when at other moisture states. Then you can still use that hypothetical moisture content, that W value for different cases to solve for that saturated density or the normal density in that case. And if we plug this in, then you would see it's the same thing as before, the 2.02 megagrams from up there. So again, that's an important one that you'll see. So I already showed this, again, the same ranges. What we know so far, we have our dry density, but now we also have this in a relationship with the void ratio. And although we assumed the volume of solid is equal to 1 to derive this ratio, this relationship is good for whichever, any type of soil. Like you don't have to assume anything. So if you're given a problem with the void ratio and you're given a problem with the dry density, then we can find the density of solids, or vice versa. You can use that in any case. We already know our void ratio. We also know that it is related to our porosity through this equation. That's another helpful tool. If you're given porosity, then you can find the void ratio, vice versa. The porosity is known. And again, you can use this one to find either one, and the degree of saturation too. For our total densities, know that in general, our density, our natural density is equal to the density of the solid plus times 1 plus the moisture content. And then we divide that by 1 plus the void ratio. That's derived from this equation, but it's still used regardless of our volume of solid. If we have a volume of solid, not 1, then we can still use this equation because that was just used to derive it. The other ones that we know then also is our density is equal to our dry density times 1 plus our moisture content. And then also the saturated is equal to the density of solids plus 1 plus the moisture content when S is equal to 100, so fully saturated moisture content, and then that divided by 1 plus E. So again, we're using densities here. Density is normally used when we are showing SI units, and that's mass divided by volume. But these relationships are the same if using unit weight. And unit weights are gammas. Remember, gamma is just the density times the gravity, or the acceleration constant of gravity. So for all of these here, we can still plug in gammas and it's the same thing, same relationship. So just remember that. They're used interchangeably. So same relationship because we're just multiplying gravity by both sides, and so it cancels out. So since we see that these are all kind of related, and you'll see that there's a lot of correlations between the two, understanding how to fill out the phase diagram is important, but there are relationships and equations that you can use. There's one super important one that is a relationship between pretty much all the parameters that you will need as a geotechnical engineer. So for this one, let's see how we do this. So saturation, this is just the percentage of the volume that is filled with water. From this, if we know our mass here, our volume of water, and since we are assuming this is just one whatever cubic meter, for example, or something, we know is the moisture content times the density of solid times the volume of solid from right here is equal to the density of water times the saturation times the void ratio. Because again, the saturation, S is equal to the volume of voids, the volume of water divided by the volume of voids. So this right here, if our total volume of voids is E, our volume of water, so this volume of water is equal to S times E. That's where this value is coming from, right here. So if we manipulate these around and knowing the density of water is 1, and then the density of this is GS, our specific gravity. Basically, the relationship that it boils down to is this: our specific gravity times our moisture content is equal to our saturation times our void ratio. So really basic equation, but super helpful to relate these 4 terms. So a way that you could remember this, you can show it in a bunch of different ways. The way that I remember it is this: SE equals WG, so it says sewage. So SE equals WG. There's another one. Let's see, let me write it in a different color. This one is not historically correct, but you could say George Washington equals soil engineer. I don't think there's proof that was a soils engineer, but there wasn't proof that he wasn't, so we can just go with that. So GW equals SE. If you could remember one equation, if you're a geotechnical engineer or not, this would be the one to remember, because it's going to be super helpful if you are given 2 or 3 of these conditions, then you can relate them and then solve for any of the other ones that you may have. The important thing here too is a lot of times when you're working, especially in Florida, what we do is we assume the saturation is 100% because it's below the water table. So if our saturation is 100%, then this equation becomes easier because it's just equal to, so let me write it up here. If S equals 100%, then it's just E is equal to GS times W, right? Because the 100, the S is equal to 1. And so this is even better. So yeah, this is an important one that you'll see in this class and through the future, and definitely on the FE and the PE. Like this is something that is a relationship. They'll give you a crazy looking problem with a bunch of different void, whatever, and you have to you think you have to go through all these steps to solve for the void ratio when really you could just apply this equation and be done with. All right, so that's it for this one. We'll start, yeah, we'll touch on the relative density next week. We'll go over more examples before your homework's posted. So if you guys have the lab section, we'll try to start at 9 a.m. if that's cool with you guys. So head over, everyone know where it is? Cool. Yep, yeah, the geotech lab on the first floor.